All right, so today we're going to be doing day 16 in Advent of Code. The first part of this challenge is that we get a grid and we have a starting position and an ending position and supposedly some reindeer are racing, and we want to see, okay, what's the most efficient path that the reindeer can take. But we don't just see the most efficient path directly, we also calculate the most efficient path with some specific calculations, and the calculation is for every step that we move in a direction we add 1 to a total, and for every time that we turn we add 1000 to the total. So technically what we're looking for is for the most part just the least amount of turns that we can do to get to the ending position if there are severals, and we want to return the least amount of points that we can accumulate to be able to get to the end. And if there are several, then of course return the one that has the least amount of points. So here's one example. In this case, we can get the fastest way through here. And if we go this way, it has more corners to take, so it's more points. So then it is not the fastest one. So that's why it only shows this. And we also have to keep in mind that the starting position, it faces east to begin with. So the first move we have to do is actually turn left here, and then we can move up, move up, move up, move up, turn right, move right, turn left, and so on and so forth. And we have to keep that in mind when we make the total. So there's more examples of how this works, and if there are several paths, we can just see in part 2 there are several paths that we can take, for example, and we'll go into that soon. But if there are several paths, we just care about the one that costs least to get there. And if there are several that cost the same amount, the least, then it doesn't matter because we just have to return what is the lowest score. So to be able to do that, we take the input that we get from here. If you scroll all the way down, you should see your own input file. It's different for every user. And we can see that here in the corner somewhere there's a S, so that's the starting position. And all the way on the top right, there's the ending position. And we don't have to see exactly where it is because we're going to find it anyways. So we open the file, we put everything in lines. I define a grid, and this is a 2-dimensional grid, and we do this by saying to make this list, and we make this list for each number in this range. And we do this with a for loop because if we don't, then each row will be a copy of the last one in memory. So when you update one row, all of the rows get updated. We don't want that. So when we do it with a for loop, it actually makes a proper 2-dimensional grid. So that's how you can do that in Python. Then what we want to do is to format it. So I get rid of all the \n, so new line characters, and we can just do that by splitting wherever we find the \n, and then it's going to be the last character, so whatever comes before is what we want. So I keep the 0th index, so that's just a way of saying to remove the \n. Then I keep track of the columns and the rows so that I can add it to the final grid. I add whatever element I see. And if I print the final grid, you will see it will just be this, but each character will be 1 index. Then the next step is to find the start and end positions, and we do that by iterating through the rows and the columns, and we start by having start and end being nothing. And whenever we find at the specific row and column, if we find a S, then it means we have found the row and column where S is at, and we store the sort of XY coordinates, not XY, they're rows and columns, but we store it in start, and we do the exact same thing for end. So now we have the start and end positions. Now we want to define the directions that we can go in, and these directions are in rows and columns. So if the first thing is a row, if we are at a specific row and we go -1, it goes up because the rows always begin from top to down, and 0 in the column direction. So this just means go up. This one means go right, this one means go down, this one means go left. And you can also think about it in terms of north, east, south, and west, because in the question it says that reindeer starts with facing east, but in our case east is just 1. So we have the start state, which we know because we found the start tile or the coordinates, and we say 1 for the direction. And what we want to do to be able to solve this is we're going to implement Dijkstra's algorithm. and it's a pathfinding algorithm. There's a lot of them that you can use. You can use the A-star algorithm and a lot of other algorithms, but we're just going to be using Dijkstra's algorithm for today. And I have a GIF here, and if we start here, you can see that it searches for different ways to get to a certain path, and if it finds a cheaper one, it updates the cheapest way to get there, and then it keeps searching in different ways to get to different places, and it always keeps the cheapest one. And once we get to the end, then once we found the cheapest way to get there, so there's also another path that could lead us there. So now we see that the 18 is the cheapest way to get there, and we know that that is now the cheapest way to get there. So that's Dijkstra's algorithm, and we can implement it with a priority queue. And we do that by importing a heap queue. You can also implement this yourself by just coding a priority queue, but we won't be doing that for this video. So we have a dist dictionary, and then in the start state we want to say, okay, how many points away are we? And in the start state it's 0, of course, when we're facing east, and then we have the start state that we give to the priority queue, and then we keep going in the priority queue and adding a new position that we find, and every time that we've used the position we pop it and we go to the next place that we can search. So we keep searching, we keep traversing through the tree, if you will, until we find the end solution. And that is the first thing that I've put here. So if we found the end, if the row and column is the same as the row and column of the end, then it means that we found it, so we just want to print the current cost. But the first thing that we do is we pop the thing that we're looking at right now, and we either move forward, we turn left, or we turn right. So if we move forward, it's pretty straightforward. We just have to get the new directions, which we get from the directions and dir, and we have defined them previously to know, okay, how much do I have to move in the row and column to go in a specific direction that we want to go into. And we do that for the new rows and new columns, and then we have to be sure that, okay, we're not going outside of the grid in the rows, and then we're not going outside of the grid with the columns. And also we have to check that it is not a hashtag, because we can't move into a wall. So those are the cases that we have to check for. And then we add 1 to the new cost, since we're just moving one step. If we're turning, it costs 1,000, which we will be doing if we don't move forward, if we have to turn first. Then what we do is we check, okay, if the new state that we have now, if it's not in dist, so if we haven't already visited it, or if the new cost that we have right now is lower than the previous cost, then we want to add the new cost, and basically how we got there. And we do heap push, priority queue, the new cost, and the new state. So this way we add this new path that we've taken. Then if we turn left, we do something similar, but with the current cost we add 1,000, and we only add the current cost if we see the same type of if statement, if it's not already in dist, or if the new cost is lower than the current cost, because we always want to find the cheapest cost to each node. So if we want to get to this node, if it's 9 right now, but we find a 7, then that's what we're going to keep. So we can do the same thing for turning right, and then we do heap push again to be able to store the new location that we found, and then we keep doing this until we find the end. So this thing will keep looping until the rows and columns are the same as the end. And this means that since this is a priority queue and it always takes the cheapest way to get there, so the priority queue is sorted by the cost of getting to a certain place. So if the priority queue has nothing cheaper than the end, then it will give us the end rows and columns. So it means that there is no cheaper way to get to the rows and columns. So then we are sure that we have found the solution, and we can just print it. So if I run it, the answer is 135,512. And if we look at the answer over here, we can see that it's correct. Now for part 2, what we want to do is not only see what's the fastest, shortest path and the cheapest path, but we want to see, okay, if somehow there are 2 paths that cost the exact same amount and that amount is the cheapest way to get there, then we want to store all of the paths that are the cheapest. So we can either go down all the way here in this example, or up and then up, or up and then down, or down and then up. So there's all sorts of combinations of ways that we can traverse this, and apparently they all cost the exact same to be able to get to the end. And what we want to do instead of calculating the points, we want to just count, okay, how many tiles have we traversed through? So how many tiles are the most optimal? And that is the question that they ask us. So if we go to part 2, a lot of the implementation is the same. We format it, of course, and then we have to find the start and end. And then we also use a heap to be able to, in a priority queue, to be able to find everything. But we have a couple of extra things here, which is a previous states, which is useful when we're going to backtrack. So once we've found everything, we also add it to the previous states. So if we found a new place that we're visiting, we add the new state and then the current state, so we can find the previous state later. So if I scroll down, here we can backtrack through the states and distances, and we do this and we append to the states if they are equal to the end. So this means that if there are several ways to get to the end, where's this picture? If there's 2 different ways to get to the end, and we've stored that, okay, there's several ways to get to the end into the distances, then we want to iterate through all of them and then see if they are the end and append them to the end states. Then once we have the end states, we iterate through every end state and we backtrack the end state. And what do we do in backtrack? We just take the state, and we take its row, column, and distance, which we don't need, we won't be using, so I'll just set it as underscore, because otherwise it's going to say that, well, it's trying to unpack 3 values, but we only gave it 2, so it's going to give us an error. So I just set the underscore even though we don't use it here. So we added 2 tiles in best paths, and it is a set so that we don't get any duplicates, and we add the rows and columns. And then for each parent, because I made a for loop here because it is possible that a path, so if we take this sort of path to get to the end, it is possible that another path somehow crosses it, maybe even several times. So here, this one will have several parents. It will have this parent over here, and it will have this parent over here. So there's several ways to traverse it. So we have to traverse it in all kinds of ways, and we have to keep track of all of the parents. So we iterate through all of the parents, and we use the get for the dictionary here, just so we don't get the key error, and it returns an empty list if there is no key. And then we backtrack this parent again and again and again, and we keep adding it to the tiles in best paths. And then once we found all of the tiles in the best path, we just set it to best path count and we print it. And I've tried to visualize it as well, and I will show it in a second. But if we run it, we get 541. And if we go to the website, that is the correct answer. And I've tried to visualize it with a pillow and image and image draw, but something was wrong in the math that I've done. It's my first time using this library, I'm not too used to it, but maybe in the future I'm going to make some visualizations, especially if there's grids and maps. But the grid itself displays correctly, it's just that the path doesn't display as it should. So I won't be publishing this to the GitHub. So that was part 1 and part 2. Now for the time complexity of part 1, we have n, which is the number of states processed. So how many nodes were explored in the priority queue, and then we have m, which is the size of the grid if we count it as rows times columns. Then the time complexity will be n log n and then plus m. And why is it n log n? Well, it's because Dijkstra's algorithm, it has to sort every new thing that comes in. So sorting it takes n log n. That's just how the priority queue works. So there's no better way to actually sort a queue or a list than n log n. That is the best possible way that you can do this. And then the space complexity is just m plus n, so it's not too bad. So for this implementation, I'm pretty happy. And now for part 2, the time complexity, it's pretty much the same, except that we also have p, which is tiles but it doesn't really add too much to the time complexity. So it's going to be n log n as it was before, and then m, and also the p. But basically we can just call it as n log n because those are the most significant things. And for the space complexity, it's also the same, but we just add p here. So it won't be too much worse. So that was the space and time complexity of both parts. Now, if you guys want to join the leaderboard, I will leave the code in the description if it can load. And yeah, thank you for watching. Happy holidays and see you tomorrow.